Ask any engineer building with LLM agents, and they will point to the exact same failure modes. The agents hallucinate multi-step plans, forget crucial context, select incompatible tools, and tangle multi-agent communication. Pushing a massive context window or a larger parameter model at the problem does not fix it. The model gets smarter, but these specific systemic failures continue to occur. The root cause lies in the architecture. Current agent systems rely entirely on sequential text as their native foundational substrate. Sequential text, like prompts, chat logs, and flat lists, inherently lacks structure. It does not explicitly encode multi-step dependencies or strict operational compatibilities, forcing the agent to guess the relationship between items on every single pass. We solve this by moving to a mathematical graph. Instead of isolated lists, entities are defined as nodes, and their exact relationships are explicitly mapped as directed edges. This is the core thesis of the Graph-augmented Large Language Model Framework, or GLA. It replaces opaque text modules with explicit, queryable graph structures. The operational advantage exists within those new connections. Graph edges carry crucial relational information that flat lists throw away, turning an open-ended inference task into a structured traversal. Transitioning from flat text to graph structures replaces exhaustive reading with targeted routing. It is an architectural requirement for reliable AI. This diagram outlines the standard single-agent architecture, a central reasoning LLM core flanked by three distinct components: a planning module, a memory module, and a tool-using module. As task complexity increases, baseline module performance degrades. Zooming into the tool-using module reveals its scaling bottleneck. On the left, the baseline failure, scanning massive flat lists to guess tool compatibility. On the right, the solution, a connected tool graph. Systems like ControlLLM implement this tool graph by permanently encoding proven tool chains and data dependencies directly into the edges between the tool nodes. The computational efficiency is immediate. The LLM simply follows an established edge to locate the next compatible tool. This directed, hot-based traversal bypasses the massive computational cost of cross-evaluating every individual item in a flat list. Tool graphs eliminate exhaustive scanning because they make tool compatibility a structural feature rather than an ongoing inference task. Shifting focus to the planning module, we see a similar struggle to handle multi-step dependent tasks. Standard linear prompting, like chain of thought, collapses entirely when an agent is forced to backtrack from an error or evaluate parallel requirements simultaneously. We fix this by introducing the workflow graph. This structural upgrade replaces linear prompting by converting the steps into a directed acyclic graph, or DAG, which branches out into parallel subtasks. Advanced implementations use Monte Carlo tree search algorithms to optimize this workflow graph. Within the graph, executing a topological sort structurally blocks step C from executing until steps A and B are verified complete. Workflow graphs force the agent to respect dependencies structurally, eliminating hallucinated execution orders and skipped steps. Inside the memory module, the standard solution has been to attempt to remember facts by simply maximizing the LLM context window. But massive context windows introduce severe retrieval noise and dramatically inflate the compute costs per query. The knowledge graph replaces this by acting as an external factual store. Entities are explicitly mapped as nodes and their relationships as edges, allowing a search query to hop across exactly two edges to find a specific fact. Information retrieval transforms from a full-text semantic search into a targeted, hot-bounded lookup. Utilizing explicit knowledge graphs structurally grounds the agent in verified data, reducing the occurrence of factual hallucinations. Expanding the architectural scope from a single agent to a large-scale multi-agent system exposes a new set of scaling problems. When multiple LLM agents attempt naive, unrestricted communication with one another, the immediate result is complete broadcast chaos. The solution is the agent coordination graph. In this architecture, individual agents act as nodes, and the edges dictate a strict, non-overlapping communication topology. This rigid topology drives system orchestration by establishing predictable, collaborative workflows between specific agent roles. Analyzing the graph structure also allows developers to identify and prune redundant agent nodes, increasing overall system efficiency while maintaining workflow integrity. This structured communication acts as a verification substrate. With agent roles fixed as nodes, graph neural networks can actively monitor the system's message flow. If an agent outputs anomalous signals, the GNN detects the structural deviation from the healthy topology, instantly flagging the corrupted behavior before it propagates. Agent coordination graphs provide the mechanism to reliably scale multi-agent systems, converting conversational chaos into a defined, verifiable architecture. We can map this entire landscape of graph-augmented techniques across both single-agent and multi-agent systems. This three-axis taxonomy categorizes GLA research, mapping the module on the x-axis, graph type on the y-axis, and structural benefit on the z-axis. For example, the AFlow system maps directly to planning, workflow, and efficiency. Across all implementations, these graphs deliver four overarching structural benefits: reliability, efficiency, interpretability, and flexibility. The technology does have limits. Currently, there is no unified meta-benchmark for comparing GLA directly against flat models. The benefits are structural rather than definitively quantified. The most significant operational constraint is that almost all implemented graphs are strictly static. They are defined entirely at design time. The future open agenda for researchers requires developing dynamic, continual graph learning, systems that adapt their edges based on runtime experience. This also includes developing multimodal graphs as the next frontier to support fully capable agent systems. A smarter LLM cannot query a flat list for compatibility, because compatibility only lives in the edges between items. Moving from opaque text modules to explicit, queryable graph structures changes the fundamental operation of an agent. It replaces the effort of constant reading with the reliability of structural routing.